Hi everyone, very excited to be here and thank blocks for us. I'm Adi, I'm looking for systems and I will speak to you today about and specifically the body problems of rollups and some ways we're trying to mitigate this problem. Let's start with a very simple example. Just like here, players, these are like two kids in the backyards in the 20 minutes. It's a very simple game. Kids get the all it's quite good. It's not fun. But we should all go with more. New games. We can make this significantly more. Simply just one player. And if we allow the players to move or become around, change the position, control the ball block through any of the other players. And additionally, we also allow them to have multiple baseball in their hands, then it gets quite chaotic. Like imagine being in this game where the other players are fastly throw multiple balls at you, it can be quite. So this is chaos. Any definition. There's two policy or three systems, initial systems in one. And it's also, in my opinion, one of the simplest ways to explain what the three-body problem is. It's chaos. It's a system which, first of all, you cannot really predict what it will do next. Even if you're inside the system, or it's even more secure outside. I'm mentioning this because I think it's a pretty insightful way to understand a bit, to get a grip on the complexity that ROMs face, especially if they affect being central. So the three bodies that actually make up the centralized rollup system are these three, but they're very basic. We have L1s, and I'm just representing them here by no. We have a sequencer, again centralized, and we have execution of those. And just like with layers, in the earlier example, each of these three systems do pretty much whatever they want, and they need to find ways to stay in check. And in the middle, we have user transactions. And the goal is that the user transactions need to be able to make through this gate of the three bodies. And this, of course, I'm abstracting over a lot of data, but I'm just speaking very high level. We can also take into the perspective the users. The users, they count and they try to use the system and they throw their transactions to the system. People in this analogy. And sometimes, because the system is so unpredictable, those people will just fall. They never make it to the system. You're there and you're frustrated because it's actually not good. Right? So you can have an inconsistent state across the two systems and lose some of the transactions. And developers have somewhere they're all as well, and they're frustrated because there's one system. In this chaotic kind of system where you can predict to happen next. There's also eventually efficiency and costs concerns, which they are considered an issue, but eventually they get. The main question that I'm trying to ask is how can we mean? This is the problem statement so far. And if you take anything from size today is to get a bit of an understanding that these are significantly complex. Within each of these blocks, there is the system itself, and they are extremely complex. So how can we mitigate that? There's different approaches. Recently, in the last months or so, in Informal, we have been having to build one method, which we call insert kernel. This is a terminology that we just invented. So it will not be defined, and it's not even clear. But I will try to explain the why I'm considering kernel, what does it mean, just and then there's another approach that we're using, which is the model of the protocols. We try to get an understanding of well, it's protocols are incorrect before we even that. Gabriela, she gave a workshop here. She's here actually, so after my talk, go and check the one look that we found. And outcome being that we want to be able to make it easier for developers to build, iterate, understand, and have predictable systems in our state. So let's focus on Malachi for a bit. Before we get there, I just want to continue with this. I like it so much. So we have the same two bodies. We have the user at the top and the translations coming through, and I'm putting here three protocols. So each of this is a complicated protocol that runs through decentralized nodes. So it's the definition of complexity we have between execution and from some assuming here. It's a kit-based rollup. It's actually inspired from the Stargate stack. So we have the execution control layer, and once the user brings the transaction, you need to execute that, and you create a proof that yes. And eventually, that proof has to make it to the L1, because otherwise it's not really wrong. Otherwise, it's just centralized. It's a centralized data of the sum. So proofs stop, and they enter a single set, and then there's another. Well, locally it's called proof submission. And the nodes of the sequencer have to convince the nodes of the L1 to take these proofs and work. And there's another protocol that is called, in this case, forced staking update. And the role of this protocol is once also between the sequencer and the L1, the role of this protocol very briefly is to make sure that the nodes that run the decentralized sequencer are consistent with the stakers on the L1. You cannot just join the decentralized sequencer whenever you want. You have to stake some tokens on the L1 because that keeps you correct. And if you are incorrect, the sequencer can be staked in its last. So this is a POS. This is actually also how Polygon does things, if you're familiar with the Polygon POS. But kind of sticking at a high level, there's two protocols here. That's the important thing. And the centralized sequencer is in it's involved in all investment that is happening. So if you want to dig in deeper to understand what complexity is, let's zoom in the sequencer. Beside the sequencer, really interesting. There's again another instance of the the nodes of the sequencer themselves. They can write to each other, they can move from wherever way they want. This is called the Byzantine fault tolerance. It's a very well studied problem. I will not go into that problem today. But suffice to say that between the nodes of the sequencer, you have again different protocols that they move around and that keeps them moving. There's a lot of complexity again. That complexity is hidden inside the node. So let's zoom in hidden. What is inside the node? Now we're starting to see some things that seem familiar. Like many of us, we have RPC. This is the entry point, where the users will start here. Transactions. We have a module that talks to the same users, other nodes in the network. And layer, in this case, I'm going to read the example. Start with the steps towards the side post, which provides serialization, provides additional transactions, and so on. And finally, we have what we call the sequencer kernel, which is really the part that encapsulates most of the complexity that is related to coordination between the different nodes. And sequencers are not expanding. I'm trying to describe to you today, and we call it the basis for this implementation is the Telemetry consensus algorithm, and it's implemented in Rust. And it's a kernel. I'll emphasize this one again. It's a kernel because it's supposed to be small, extensible, and readable. To think of it with what kind of principle given, I got when in your music extensive experience with in community and with complexity of what it takes. I mean, things such complex code is for multiple years. It's a very tough job. And some things that have inspired us in building more guide is the last of it. And specifically, we're huge exercise in the industry and keeping the quality of the business as small as possible. So we want to be single and concise. This is very important for us. The second is we want to be split it can be. It's not supposed to be a slash number that solves all the problems of the world. And it's supposed to be efficient and powerful. So you start with what you need and then you allow other users, developers or other systems and depending on use cases to add the different features that you need instead of studying up front. That's really the problem there. You have all the possible issues. Interestingly, so I was reading a book recently, and the book is about the Unix kernel. I read these three descriptions. What is one of the three is actually false that I do, and the light of the bulb over it. The Unix kernel had exactly what the same description, the same principle in knowledge. So I'm just copying it. Yeah, and the purpose of this implementation is we want to offer long-term functionalities. So it's not necessarily some show rate. It's date or tens of digital service. And the primary goal actually is to be able to provide a platform, which we do not have yet, to experiment with different decentralization pyramids. Sequencers are just a bit. There will be other decentralization pyramids that we are going to. There's provers, there's going to be different markets that are going to be built around the CDN. And we may need other centralization coordination beyond sequences. So we're building just small kernels so that we can build other things. It's not necessarily aimed at, okay, we have one problem, solve it, and then we forget. Um, so there's a lack of experimentation actually in the field of consensus algorithm or sequence. And we want to bring in that kind of platform that allows and encourages experimentation. So that's why there's so much emphasis on small, lean, simple. And the third thing is I mentioned OMBFT and we see this complement. OMBFT is something like session or Swiss knife that's supposed to really do a lot of this. So if you're not changing and you want to just launch an L1, you just go to OMBFT and do solve any problems. But Malachite will not solve those kind of problems if you actually design it, but that's something. And this is the architecture overview on how we have integrated with an actual use case. What I want to emphasize here is that every one of these boxes, so the orange boxes and the green box, they're an actor, it's a concurrency model, or actor-based concurrency model. If any of these is familiar with kernel, you will also be familiar with the node that's at the top, and that's called a supervisor. This is more like a supervising role where in case one of the actors dies or needs to be restarted and so on. It's a very strong foundation for building fault tolerant systems together as concurrency mode. But in real strength, it's not necessarily a supervisor. It's real strength that you focus the different components and you can test each component in isolation from the others because the component efficiently reacts to messages that are coming in. So there's no shared state, the different elements. And because there's no shared state, isolating each component, they reduce problems very easily. That is its main sense. For those of you familiar with Rust, we recognize Tokyo. It's a library that's what used to build this. Underlying in the both mango and the Rust pair, we use Sleep the Beat. It's still a decision that we're not locked on, but it's good enough to get learning experience with it. The main point for building all of this, as we see there, the context and what I called host earlier, was so that we can actually get that kernel in the middle that consists of three very basic elements. I will not go into detail of what those are. I'm happy to describe it, and you can is interested. Was that so that we take the kernel, which is in the middle, and we integrate it with actual use case, and then we put it on the centralized network and run some experiments. And we've been doing that for like 3 weeks now. The main goal is actually not to get performance. But I'm showing you performance in the towards the goal of showing stability. So the bottom graph shows how many rounds the 25 validators need to reach consensus. This is an indication of how much stability there is in it. If there's bugs, if there's storage, if the system is not parameterized correctly, this is typically about 1, 2, 3, 4, if it stays at 0, it means that the current proposer of the block has matched the other nodes in the network when they were able to successfully accomplish building the block. So flat line is 0, good sign. And then the map at the top shows this 3-hour, almost 3-hour run, and the number of the blocks are increasing. And each new height is produced as time passes. Where each new block or new height consists of 1 megabyte block, roughly, and it happens every 1 to 2 seconds. So it's the same regular. If the bottom graph would have shown spikes, then the top graph would have shown less, the curve being less each time. And yeah, we don't have a full stack here, so we're not storing up to the disk. There's no write ahead. So there's different elements that are missing. Like I said, the point of the sequencer around Monolith does not provide those things. Those things were basically drivers or plugins that were attached. This is kind of the most important part. We're quite excited that we're seeing stability. We're still chasing different order cases and difficulty or different order cases in other dependencies. And trying to make sure that what we're building on top of it, the other drivers and so on, we're building on stable foundation. Well, yeah, this is a roadmap. It's still, it's a live dog, right? It's many of the roadmaps, they're not set in stone. It's not like the tablets of 10 rules. So we started development in late 23. Today, in July, we have been experimenting with 100 nodes. The box I showed you earlier was only 25 nodes. But we have runs with 100 as well. And we're basically just chasing bottlenecks and trying to analyze why is performance abilities. before we move forward with adding software. And we're trying to use persistence for building starting decentralized sequencer. So that towards 2025, it's once I finish the version of Yellow one to submit the proofs. Proofs that I mentioned earlier, you got there's integration in Yellow one, and you also need to manage the validator set is running the sensor so that this is safety project on Yellow one. We're going to try to have a testnet, which means that one that not need to run on its own, and there will be actually other sequencer implementations, and they need to be able to, they will all use under the same algorithm. Then the processor is the simplest one to implement, and what we want to choose just a bit. And we're going to add support for other add-ons like boxing and proof scheduling. And we really want to just demonstrate the first rollups. It's like it's a multi-year goal, but for 2025, we want to have that first and before that. And of course, as the years will pass, we want to see to eventually continue just this still small and internal. That it's very extensible things that one big population derivatives, such as sequencers, for rollups. And this is going to be more in the modular size, and many add-ons that consider depending on its uses. Coming back to the approaches, and I mentioned in the beginning, I mentioned quit. I will not go into details because I'm not that's I have the language and just launch the website. And again, the deadline is over here. We have a couple of other experts in the room as well, so please check it. I just want to bring attention to it, and if you're aware that it is a programming language aimed at developers, so the systems that we are reading here extremely complicated systems, and they're handling actual people's money, and so it's serious. It's not something that you just take it easy with. And it helps you reason quality system, helps you measure the missions. Really that's very important. Say I go to the website, and ultimately we want teams to be able to compose systems that are easy to integrate on. Because once we build something, we realize that the system is not what goes the next step to the next step. So it's really important to be mindful of really reiterate on the value of the businesses that you are building. And my final slide, just a bit about informal systems. So I mentioned a lot of liquid. We also contribute quite CRS. We also contribute to bringing cybersecurity there. Look, guys, really the audience, please stop thinking about multi-pop support. It's interesting or anything. If you're no operator and do what is in lane, he's a man. Yeah, women may want to get earlier. There's a couple of cosmic stuff. 14 here numbers. Then we have at least 3 of them. And we also have this adventure cycles, and by women by Origin. And we're also very active on the audits front. I mentioned earlier that security and practice are very important for us, and audits are another function. Finally, if you're interested in looking for a career, in particular if you're a Rust developer, we're always looking for and so please let me know. So I'll be back there in questions. Thanks very much. Well, you can all kind of chain constraints. Yeah, it's a complete chain. So we want to understand that there's what goes on. From the perspective of Malika, what happens is that the consensus component, Malika itself, asks for a value. And that value is in bytes. And there's no assumption about how this bytes are bigger or small they are. There's no assumption on the block, semantics, that's the seven. Because we just streamline abstract. There is role decentralized in practice right now. That you can raise. No, I'm not. There's different implementation of sequencer that I'm aware of, but none of them that I'm not looking to flush. None of them given that use under. Some of them use other algorithms or experimental algorithms, and so they go to their argument. The best. The same.